Good day, everyone. My name is Eze Gloria Chidubem, a 200 level pharmacy student in the University of Nigeria, Nsukka, and I'm the current Assistant Academic Coordinator of NFCPS UNN chapter. And this tutorial is brought to you by the members or the body of NFCPS, which is National Fellowship of Christian Pharmacy Students. So this is going to be the second experiment we'll be talking about for 300 level practical chemistry. And then this experiment, it told us that we should determine the amount of sodium hydroxide and sodium carbonate in a given mixed solution. So basically, you have your sodium hydroxide and your sodium carbonate mixed in a solution. They gave it to you and they told you to determine the amount of each of them. And one of the uses of titration is to determine the amount of a substance in the solution. So we're going to determine the amount of sodium hydroxide and we'll determine the amount of sodium carbonate. And this titration is going to be, let me just say, somehow tricky because you have to be very careful with your choice of indicator because you have a strong base here, which is sodium hydroxide, and you also have a salt, which is what? Sodium carbonate. So you have to be very careful. And then, what is the procedure for this experiment? Let me just read it from this book. It says, rinse the burette with 0.1 normal HCl and then fill it. Pipette out 25 ml. We're going to use 10 ml. Pipette out 10 ml of a given mixed solution into a 100 ml conical flask. First, add 2 to 3 drops of phenolphthalein as indicator. Titrate the solution with the standard acid until the red color is destroyed. To the same solution, add 2 to 3 drops of methyl orange indicator and further titrate the solution with standard acid until the red color is restored. And then, alternatively, titrate portions of the solution with a standard acid using phenolphthalein, methyl orange as an indicator. So we are using 2 indicators in this experiment. And then, first of all, somebody will ask, why did they say we should rinse the burette with HCl? If we rinse the burette with HCl, are we not also supposed to rinse the conical flask with a solution of sodium hydroxide and sodium carbonate? The reason why you are rinsing your burette with the titrant or whatever thing you are going to put in the titrant, in this case acid, because we are going to use acid here. In this case acid, you are rinsing it because assuming there is water in the burette and you just put your acid there, it's going to further what? Dilute the acid that you have in your burette. So you need to rinse off with whatever thing, whatever titrant, whatever analyte, whatever thing you are going to put in your burette, you need to rinse it off. And then why you don't rinse conical flask is because at the end of the day, after rinsing conical flask with your solution of sodium hydroxide and sodium carbonate, obviously you are going to have remains of that solution. No matter how you try to get it out, you are going to have remains, and that is going to increase the volume of this solution you are going to have, because in this experiment we are going to use 10 ml of the solution, and then you pipetting 10 ml and putting it inside the conical flask, you already have some, you have traces, you have solution, let me just say small volume of the solution that is already in your conical flask. So that is why you don't rinse your conical flask with your analyte. So this titration is basically going to be in 3 stages. And then I told you that you should be very careful in selecting your indicator that you are going to use. You are going to use phenolphthalein and methyl orange. In the first one, they say we should use phenolphthalein. Somebody will now ask, okay, why are we using phenolphthalein? Are we not supposed to use methyl orange? After all, strong acid and strong base, you can use any indicator of your choice. One of the reasons, in fact the key reason why you should use phenolphthalein is because phenolphthalein causes partial neutralization of sodium carbonate, which you need. If you use methyl orange, everything, you're just going to get the volume of both sodium hydroxide and sodium carbonate in the solution. It is not going to give you a distinct amount of sodium hydroxide and sodium carbonate. So you need to take this thing sequentially. It is step by step. That's why you are using phenolphthalein indicator first. So the first reaction is, they say we should titrate with 0.1 normal HCl You already know the concentration, which is your what? 0.1 normal. And obviously, we don't know the concentration of this solution given to us. So this is going to be your equation of reaction. So equation of reaction, we are going to have, this is, remember that there's a strong base inside, which is sodium hydroxide. And there's also what? A strong acid. So there's going to be a complete neutralization of sodium hydroxide first in this experiment. And it will also, the phenolphthalein will also cause partial neutralization of what? Sodium carbonate. So first of all, we are going to have this reaction of your hydrochloric acid reacting with what? Sodium hydroxide. This is acid and base to give what? Salt and water. You have your sodium chloride and your what? Water. Is it balanced? Two hydrogen, one sodium, one chloride, one chloride. How many oxygen? One oxygen, one oxygen. So this is balanced. This is your stage 1. Your stage 1. And then we're also going to have your hydrochloric acid also reacting with sodium carbonate to give what? Sodium bicarbonate. And what? Salt, sodium chloride. Is this equation balanced? One hydrogen, chloride, chloride, 2 sodium, 2. Okay. This equation is balanced. This, remember that I told you that the first titration, the phenolphthalein endpoint, this is for the phenolphthalein endpoint. In the phenolphthalein endpoint, you have complete neutralization of sodium hydroxide and as well partial neutralization of what? Sodium carbonate. So you are going to have, like in your first endpoint, just bear it in mind that is going to give you the volume of the sodium hydroxide and also half of the volume of the sodium carbonate. So that is your first titration. You cannot just say that the first titration, you titrated with HCl and your sodium hydroxide is there. So whatever volume of acid that is there is now going to be the volume of acid that is needed to neutralize the volume of the sodium hydroxide. Then no, because it's not only sodium hydroxide that is here. Sodium hydroxide is here together with this. So that is your what? This is your stage 2. And remember that this stage 1 and stage 2 is phenolphthalein endpoint. And then we're also going to have the last one, which is now the complete neutralization of sodium carbonate. So this is still going to react with your HCl. This is your methyl orange endpoint. See, when you are done with this titration and you get your endpoint, you come again. In that same solution, you add your methyl orange. That is another indicator. And then you continue your titration. That is going to give you the volume or the amount of the remaining sodium carbonate. So if this is going to be salt and carbonic acid. So this is basically complete neutralization of what? Sodium hydroxide. And then this is partial neutralization of what? Sodium carbonate. It will neutralize partially, give this, then the complete neutralization is this stage 3. That is your methyl orange endpoint. Then how are you now going to calculate these things? How will you know the volume of this sodium carbonate, the actual amount of sodium carbonate and the actual amount of sodium hydroxide? This is half of sodium hydroxide and this is another half. So the second endpoint, this is just hypothetical values that we are going to be using. So this our first titer for this is phenolphthalein endpoint. We got this, we got this, we got this, second titer, third titer, and then this is your second endpoint, which is what? The methyl orange endpoint, which is this. See, let me say that this is your burette. And then you are titrating. The first one, which is your phenolphthalein endpoint, you had your 0, your reading as 0 mil. Then you are titrating with acid. And then you used up the acid, the volume of acid, up to this point. Let's say, what did we say? Okay, that the first one is 16.2. 16.2. This is for phenolphthalein. And then remember, you continued this experiment, not like you refilled the burette. You continued this experiment with still the acid that is remaining inside the burette. And then you started your second titration. And then your second titration, let me say that your acid is now here. And what do we have? We have, hypothetically, 22.50. This 22.50 is actually the entire volume of acid that is required to carry out this experiment. Not like it's the volume of acid that is required to neutralize only the carbonate or the sodium hydroxide. This is actually the total volume of acid that you need for this experiment. So how are you going to know each one? The one, this certain amount that is for sodium carbonate and the one that is for sodium hydroxide. What are you going to do? You simply say, since this is for the third one, which is your stage 3, which is your methyl orange endpoint, and we say that methyl orange endpoint, that this is for complete neutralization of carbonate alone. We are done with sodium hydroxide, so this is for complete neutralization. So this is like half of carbonate, and this is the second half of carbonate. They are like half. Hold this one, I'll hold this one. So this one, you are going to, how you get the volume of acid that you need for neutralization of, complete neutralization of sodium carbonate. You do 22.50 minus 16.20, which is going to give you what? Remember, this is for the third one only, not like it's for everything. It's just for the complete neutralization of sodium carbonate. So you are going to be having what? 6.30. So you have 6.30 here. This is your V2. In this your volume of HCl, we just said let us call it V1. You can call it anything. You can call it A1. You can call it whatever thing that you want. And then we said that the volume of acid that is used for this methyl orange endpoint, we decided to call it V2. And we now said that for us to get the volume for only this one, what are we going to do? We just do this one, which is the last one, the entire volume of acid minus the volume of acid that you used for your first titration. If you subtract this from this, it's going to give you 6.3. Your 6.3. Then you do the same thing for this one, this and this. You do the same thing for this and this. Remember that that is for only complete neutralization. You're not going to throw away this one. You still consider this one as you are considering this one. So if you get this one, it's already work made easy. You can easily get this one. Then you subtract this from this and this from this, and you are going to have 6.10 and what? 6.40. And then that is only for this one. If you now want to find out the total amount of sodium carbonate that is present in this mixture, that is present in this solution, if you want to find the total amount of sodium carbonate, you simply do this half. Okay, since 6.3, since the complete neutralization of sodium carbonate is 6.3, it means that since it's 6.3 and we already told you that it's half, which means they are equal. If this one is 6.3, it means that the volume that is also inside this one is what? 6.3. Because for this and this, if you are using this first one, for this and this, we have what? 16.20. But inside that 16.20, we have your volume of what? Sodium hydroxide, and volume of what? Sodium carbonate. That is sum of the volume of what? Sodium carbonate. So since you have gotten, okay, the volume of sodium carbonate that is required to complete this neutralization process, okay, it now means that since I now have 6.3 here, it means that I should also have 6.3 mil inside this one. So you basically, whatever you get here, you just multiply it by 2. If you multiply this thing by 2, what are you going to have? Anything that you're going to have, that is your what? The volume of sodium carbonate. That is the volume of the entire sodium carbonate. Then if you get it, then your sodium hydroxide is very, very, very simple. That one is like very simple. So if you multiply this by 2, this by 2 is going to give you 12.60, and this is 12.20, and this is 12.8. We have gotten our what? Sodium carbonate. And somebody will now ask, what am I going to do to the sodium hydroxide? How am I going to get my sodium hydroxide? How you are simply going to get sodium hydroxide is that you can either do this last one, the volume, the entire volume of acid that is required for this titration, you subtract it by the total volume of acid that is required for the neutralization process, the complete neutralization process, the entire process, the entire neutralization process of what? Sodium carbonate. You subtract it from what? The volume of the acid that is used for the entire titration. So you can do this, subtract it from this to get your volume of sodium hydroxide. And there's also another way. If you don't want to do it like this, you can also say, okay, let us go back to our first titer value. Remember that our first titer value has what? Sodium hydroxide and sodium carbonate inside. And we have already seen that, okay, we have found half of our sodium carbonate. So it's very simple for us. You just subtract this, you subtract the first one, you subtract the volume of the sodium carbonate that is required for the partial neutralization. You subtract it from this your V1. You can either do this minus this to give you this, or you do this, you subtract it from this to give you this. Either way, any one that you like. So you are going to be having here as 9.9, and the next one is 10.3, and the next one is 10.1. I hope this thing is very clear. Very, very clear. Very clear. Just listen to this video and watch it carefully. If you watch it carefully, you are going to understand everything that I said. And then let us proceed. Because what is our aim? Our aim is to determine the amount of sodium hydroxide and sodium carbonate in a given solution. Okay, this thing, you can just take your titer value. Take your titer value. Then if you are taking titer value for sodium carbonate, you just do, you know how to get your titer value. You sum all of them and divide it by 3. 1, 2, 3. So for the volume of sodium hydroxide that you used in this experiment, the volume of sodium hydroxide is 9.90 plus what? 10.3 plus 10.1 over what? 10.1 mil. So this is what? 30.3 divided by 3. If you divide it, it's going to give you what? 10.1. Sorry, this is 3. 10.1 mil. So this is the titer value, average titer. Average titer of what? Sodium hydroxide. You can say that this is the average titer of sodium hydroxide, and you can also say that this is the average titer of the volume of acid that is required to neutralize sodium hydroxide. That is this thing that you have here. And then if you do this for your sodium hydroxide, you can also go and do it for your sodium carbonate. You get your average titer, which is 12 for average titer of sodium carbonate. You'll be having your 12.6 plus 12.2 plus 12.8. You divide it by what? 3. It will give you 12.52 mil. So that's just basically it for this table. And then if you want to calculate the normality, we're going to calculate the normality of sodium carbonate and also the normality of sodium hydroxide in this. Since we already know the amount of sodium hydroxide that is present in this mixture and then the amount of sodium carbonate that is present in this mixture, we are going to do what? We are going to find the normality of each and every one of them. We'll find for the first one, we'll find for the second one. And you know your normal formula for your normality, N1V1 is equals to N2V2. You just substitute and get your answer. Then let us do it for the sake of those that don't know how to do it. So we are moving over to the calculation of the normality of what? Sodium carbonate. And normality of sodium carbonate. Using your formula, N1V1 is equals to N2V2, where your N1 is normality of the acid, which is the titrant that you used in this experiment. Normality of acid. What did they say is normality of acid? If you are listening, the normality of acid is 0.1. 0.1 normal. And what is your volume? The volume of acid. This is basically the volume of acid that you used to neutralize this sodium carbonate, which is going to be what? Oh my god, I've cleaned it. The average titer, this plus this plus this, I think it is 12.58 mil or so. 12.58 mil. Then this is the normality of your sodium carbonate, which you don't know. Normality of sodium carbonate is what? And then the volume of the sodium carbonate. The volume of sodium carbonate is what? The volume of sodium carbonate is, the volume of sodium carbonate you are going to use in this experiment is the volume that you actually pipetted and used in the initial titration. When you wanted to start this titration, the volume of sodium hydroxide and sodium carbonate that you used, that is going to be the volume that you have here. So which is going to be what? That is the volume of the base. What did we use? We used 10 mil. So if you are making your, this is what you are looking for. If you make N2 the subject of the formula, you have N2 is equal to N1 V1 over V2, which is what? What is your N1? Your N1 is 0.1. What is your V1? Your V1 is 12.58. What is your V2? Your V2 is 10 mil. Don't mind my handwriting. 10 mil. So if you divide this, what you're actually going to have is 0.1 normal. Then you might proceed to calculating the strength of sodium carbonate. What do we say that is the formula for the strength? Formula for strength is equal to normality times gram equivalent weight, but you have to find the gram equivalent weight of sodium carbonate. And how do we find gram equivalent weight? You do molar mass over valency. And remember, we determined the valency of sodium carbonate initially in the previous experiment, and we said it's 2. So there's no point determining it again. We'll just input 2 and we are equivalent weight is what? Molar mass. Here you are checking for the molar mass of sodium carbonate. Remember, you have been working with sodium carbonate. We have determined the normality of sodium carbonate as 0.1 normal. So everything that we are doing this side is just concerned about sodium carbonate, we still do for sodium hydroxide. If you just follow the same process, you get for sodium hydroxide. So equivalent weight is what? Molar mass over valency. Valency of sodium carbonate, as we said, is what? 2. What is the molar mass of sodium carbonate? The molar mass of sodium carbonate is 106. 16 gram. 106 gram. So 106 divided by 2 is what? 53 gram. Equivalent. So this is your equivalent weight. So moving over to strength. Strength is what? Equivalent weight. Equivalent weight multiplied by what? Normality. And what did you say our normality is? Normality is 0.1. What is our equivalent weight? Equivalent weight is what? 53. 53 multiplied by 0.1. That is going to be the strength of your sodium carbonate. So that is just all. And then if you want to do for sodium hydroxide, you just follow the same process. You calculate for the normality of your sodium hydroxide, and then it's just that here you now have a different volume of acid, because there's a different volume of acid that is required to neutralize sodium hydroxide. So you are going to have a different volume of acid, which is your average titer for this side. This plus this plus this plus this. That is what you're going to have as your V1. And then what else are you going to change? In your equivalent weight, you're going to change the molar mass, because the molar mass of sodium carbonate is not the same thing with sodium hydroxide. The molar mass of sodium hydroxide is 40. So you just change it and then you get it. And then you still come here and calculate for your strength. You do your normality, the normality that you were going to get in your sodium hydroxide multiplied by your equivalent weight, which is actually, let me just, okay, the valency. You know that the valency of sodium carbonate is what? 2. The valency of sodium hydroxide. Remember what I told you? That if you want to find the valency of this sodium hydroxide in terms of, okay, if you are looking for equivalent weight in terms of what? A base, it is molar mass over valency, which this valency is the number of replaceable hydroxy ion. And then this is going to be, if this ionized, you have your sodium and you have your OH minus. And your OH minus, obviously this thing is 1. So the number of replaceable hydrogen in sodium hydroxide is 1. So that is going to, you are going to have 1 here in the case of working with sodium hydroxide. So that's another difference. You have 1 here, you have 40 here, which is just that 40 divided by 1, which is 40. So your equivalent weight for sodium hydroxide is going to be 40 grams. Then you just come here and calculate for your strength, do the normality, whatever normality that you are going to get there, multiply by your equivalent weight, which is 40. That is your what? Strength. And remember to always put your unit for the strength. Unit for your strength is what? Gram per liter. So that is it for this experiment.